Okay, okay. Yes, yes, yes. Good, very good points. No. I don't want. I don't want to be insulted. So, uh, you're gonna need a blank sheet of paper to keep notes on. Today's a very exciting day. It is. Today you see something that I think you're really gonna like a lot, and it's not that difficult once you see how to do it. Okay, so the idea is you guys have been able to find area bounded between a curve and the x-axis. Well, right now, the question is, what if we took that area that you found and we revolved it around the x-axis to make a three-dimensional figure? Could we find the volume of that? Yeah, they wanted to learn some things that we were doing, and they're like, what is calculus? Everybody wants to know what is calculus because it sounds complicated. And lots of kids in Algebra 2, kids in pre-calc, kids in Algebra 1, they're like, what is this calculus thing? Could I take calculus? And you gotta try to tell them all the important things you need to learn in pre-calc and stuff in order to prepare you for calculus. So that you know that sine is equal to 0 at 0 and 180, and that cosine is equal to 1 at 0 and 180, and things like that. Or I'm sorry, just 0 and 360. What's that? Well, one definition. Calculus is the application of the method of exhaustion. And we are going to see that today, the method of exhaustion. And here we go. Basic example. Okay, we start with that basic shape. Very, very basic shape. We have a function, namely the square root of x, and we're going to bound it with x equals 4. And we're going to look at that shape, and we know how to find that area. Uh, the area is the area is rather simple. We could say that the area is equal to the integral from what to what? From 0 to 4 of my function, which is square root of x dx. No problem, right? So we've learned that, but we want to change the problem because right now that's too easy for you guys. That's far too easy. So what we want to do is watch what happens here. I'm going to take this shape and I'm going to try to draw what it would look like if I revolved it around the x-axis. Do you see that shape? If you were to describe that shape, what would you describe it as? Okay, kind of a cone. I'm going to call it half of a football. That's what we're doing right now, young man. So, um, what I would like to do, and this is really the theory portion of what we're working on. And so what I'm going to do is I'm going to slice off a disc. you will often not like to slice off a disc. You will often like to skip this step, and you will do other things. And there will come a time in a week where you will wish that you looked at the disc or the washer or the cylinder or whatever it is that you were supposed to cut off and look at it. So I'm going to slice off a disc. And I'm going to show that disc right here, okay? I'm just going to take this small disc, okay? Almost like a ham. I'm going to slice off the end of it. I cut it off. This is the piece I cut off. Tell me, if you wanted to find, let's start with the area of this slice, what would we say? What does the shape look like? Let's just look at it as two-dimensional. It is a circle. I know that it looks like an oval, but if we think about it, this is a slice of something we have revolved completely around the x-axis. It is a circle. And how do we find the area of a circle? So the area of this is going to be equal to pi times our radius squared. So what we need to do is we need to identify what is the radius. Okay, well, right here, the height of the function is 2. But remember, we chose to slice it here. We could have sliced it anywhere. So the radius is equal to the height of the function. How would you find the height of the function? How did I find that it was 2? I plugged it into the function. So the radius is equal to whatever the function is evaluated at that spot, right? So what is the radius in this situation? The square root of x. So the area is equal to pi times the square root of x quantity squared. Now we'll simplify that in a second. I just want you to see it. Now we're not finding area though. We are finding what? Volume. Well, in order to find the volume of this, I would simply multiply it by the width. What do we use to represent width? dx. So this width right there is dx. So the volume is simply equal to pi times the square root of x squared dx. You tell me, in light of the method of exhaustion, how many of these type of slices would we like to add up to find the entire area? Infinity. What do we do? What do we use in order to add up an infinite number of slices? The definite integral. And so this becomes very, very straightforward. The volume is equal to, we're going to add up an infinite number of slices. We're going to start at 0. We're going to go to 4. And these slices all have a volume of pi times the square root of x quantity squared dx. That is going to be the volume of our half football. Do you see where I came up with this? pi times r squared, pi r squared, and then dx was the width. That's how we get the dx in there. That's that little width. So let's integrate it. Volume equals the integral from 0 to 4 of pi x dx. Take the pi out. Volume equals pi times the integral from 0 to 4 of x dx. That's a pretty simple integral to calculate. We have volume is equal to pi times x squared over 2 evaluated from 0 to 4. 4 squared is 16 divided by 2, 8. That's it. We found the volume that quickly. How did we do it? We summed, instead of an infinite number of rectangles, we summed an infinite number of discs. The infinite number part is the definite integral. That's what the definite integral does. Look, the definite integral is equal to the limit as the number of rectangles approaches infinity. So we substitute our integral for an infinite number of rectangles. That's what it does. It's a beautiful thing. Isn't it a beautiful thing, Kyle Ohms? It's pretty beautiful. It's pretty beautiful. Okay? So we will write the rule down, and this is what you need to know. Volume is equal to the integral from A to B of the area of an object times the width. The area of an object times the width is a volume, and we add up an infinite number of those to get the entire volume. Just like we used to add up an infinite number of areas of rectangles. And that's what we do. So the formula is that simple. Generally, all you need to do is just figure out your radius and then square it. So we're going to take baby steps today, and we're going to try more difficult ones later on, because there are shapes that we get that, like bowls, that have, portions cut out in the middle. So we're going to cut the inside out of some of these objects. You can't draw it on your calculator, but I do know that Mrs. Rubel has some really good software that shows calculus and algebra in motion, so you guys can get a better visual of this. And I'm going to meet with her either tomorrow or Monday, and she could show me a software. But she said that really helped her calculus class last year see how that happened. So actually, Grady's going to go learn it tonight and then come back and demonstrate for the class tomorrow. How about that, buddy? He's excited. Okay. Let's try a different example, and then you guys could try one on your own. Example 2. Question. Yep. 8 pi is the volume of the half football, the cone, the whatever shape you'd like to call it. Right. So part of the challenge is being able to draw the graphs. So I'm drawing the graphs for you ahead of time. And what we want to do is we want to actually look at, a lot of times what the book will say is, let's look at the region bounded by, say, the x-axis, the y-axis, namely the first quadrant, as well as these equations that are given. So I have another one where we have y equals x squared plus 1, and then x equals 2. And so what we could do is we want to find the volume when this is revolved around the x-axis. Now note that we have options here. Later on, we're going to revolve this around the y-axis, and we're going to get something different looking. Yes. The directions would say that. The directions will specify. They will say, for example, the directions of your book right now for problems like this, they say first quadrant, restrain to the first quadrant. So here's what I like to do. I like to start by just drawing it, revolved around. Good. Now, remember, okay, we like to say volcano, we like to say trombone, and just to be able to delineate which is which, understand that this is solid all the way through. This is solid all the way through, okay? So there's no hole in the middle. This is solid all the way through. So, again, all I'm going to do is I'm going to cut off a slice. What is the width of my slice? How wide is this thing that I cut? It's dx. The width is infinitely small. It's a very, 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 very small thing that I'm cutting. Remember, we want to work towards a width of 0. And my radius I have to find in order to find the area of the top. What is the area of this object? We have area is equal to pi r squared of a circle, which is the shape that we have. What is my radius? In this case, it is simply x squared plus 1. Because this width right here, this radius right here, is the same as the height of the function. And if I want to find out the height of the function, I just take my x value and I plug it in here, and I will get x squared plus 1. So for any x value, like for example at 2, 2 squared is 4 plus 1 is 5. So if I cut off the end, this radius right now will be 5. How did I get that? I plugged it into the function, x squared plus 1. So now I'm ready to go. Volume is equal to, you guys tell me what to put next. The integral of, from what? 0 to 2 of pi x squared plus 1 quantity squared dx. That is going to be the volume of my shape. That is what I'm going to revolve. Yep. And you guys, again, when we have holes in the center, like say a trombone, which we can do, when we cut the disc, when we cut that disc, we're going to get a washer. We're going to get a washer because there's going to be a hole in the middle. So our radiuses, our methods, our geometry will change. So we're doing the most basic examples here right now. And we're going to practice them. We're going to get good at them. And we're going to move on to the next stuff. So my volume, as Taylor Blake mentioned, I'm going to pull that pi out front. And I will integrate from 0 to 2. And I'm going to square this out. When I square out x squared plus 1, I get dx. Therefore, the volume is equal to pi times the antiderivative, which is I'm going to do it by hand. I'm going to find common denominators of 15. Oh boy, 96, 80, and 30. I've got 176, so 206. 206 pi over 15. So whatever that comes out to in terms of a decimal or as a mixed number, if you want to express it. Uh, it, it's not, because it's neither divisible by 5 nor is it divisible by 3. So I know that this is simplest fractional form. And that's the answer. You guys ready to give this a shot? You try a problem. There you go. There are your two functions, not functions, excuse me, your two kind of equations that give you your boundaries. We have y equals 1fx plus 1, and we have x is equal to 4. And what I would like you to do is the area formed by that in the first quadrant, I'd like you to revolve it around the x-axis, and I would like you to then determine the area once you've done that. Yep. So this area right here, never mind after quadrant 1. Never mind back here. Just going to focus on this space here. Which, to brighten everybody's day, here's what I will do. I will show you that area. That is for you, Chelsea Peterson, especially for you. And Michelle is watching this tonight, so special note to Michelle. Thanks for the cake. Nice job. Let's try this. Okay. So try it again. This is our shape. We are going to simply look at this area right here. And we'll go from there. Rotate about the x-axis. What's that? So you're going to revolve this around, and you're going to have to slice it, right? And as you slice this, my radius here is different than the radius here, which is different than the radius here. So same type of process. Don't get too fooled. Same type of process. The radius, 99% of the time, is going to rely on the function. And then if we get this, then I would like to do one more that's slightly more difficult, and that will really, really help prepare us for tomorrow. Okay, boys and girls, we will end here today. We'll go through this, and we will practice this tomorrow, and then we will start a washer method on Monday. Again, so the questions come up, maybe I didn't square it, maybe I didn't do this, maybe I didn't do that. Understand that we are starting with the very basics. Shh, guys. Shh. So what we want to do is, as I draw that disk, it just helps me think, what is that radius? And the radius happens to be, if we were to evaluate x, we would just plug it into the function, which is negative x squared plus 3x. That is our radius. And so the area of this, so now I need to think, okay, I got to find the area of this disk, which is pi times my radius quantity squared. And in order to find the volume, I could simply integrate my area. And so I'm going to integrate from 0 to 3 of pi times negative x squared plus 3x quantity squared dx. So the first question is, do you have your integral set up correctly? So that's how we set it up. Then the second question is, after this, right now we're doing algebra. Well, so we have the volume is equal to pi times our integral from 0 to 3 of, we square this out, you should get x to the 4th minus 6x to the 3rd plus 9x squared. If we square that out. Chels? That? Yeah. Okay. Then now we take the antiderivative. Volume is equal to pi times x to the 5th over 5. Got to take the antiderivative now in order to get rid of our integral. Minus 6x to the 4th over 4, or 3x to the 4th over 2, plus 9x to the 3rd over 3, or 3x to the 3rd, evaluated from 0 to 3. You plug in your 3. We get 243 over 5 minus 243 over 2 plus 81. And when you do that on your calculator, you should come up with 81 pi over 10. So we could practice a few problems like this tomorrow for an assignment. That is where we'll be. If you got questions how I got that answer, raise your hand. I will come around and help you.